So next speaker is Meriem Behiri, and she will talk about surfing long waves to discover old dusty treasures. So can you share your slides?
Yeah, here I am. Can you see my screen?
Yes.
Okay. Yeah. So, hi everyone. I'm Meriem Behiri, and I'm a second-year PhD student at SISTA under the supervision of Andrea Lapi, Marcella Mattardi, and Margherita Taglia, who is in the University of Bologna. And actually, you've already heard a lot about my main collaborators, like Dino D'Amato, Marica Giulietti, and Martina Torsello, and you will also hear a talk tomorrow by Fabrizio Gentile. So my talk is actually split into two main parts. At first, I will try to convince you of the power of the radio selection. So why should we care about using radio observations to look for high redshift galaxies, in particular the dusty galaxies, so the typical ALMA targets actually, and so why are important the synergies between these bands. And later I will introduce you, actually already Quirino D'Amato told you the first day, but I will go deeper under the shores, so digging in the deep field of our brand new survey. So first, why are we doing it? Why should we care about studying on a radio perspective the high redshift universe and the galaxy formation? So first of all, this is the very well-known Maddow plot saying the star formation rate density, thus the star formation rate per volume, for conveying volume. And as you can see by this very famous picture, actually, the part at higher redshift, even though this has already improved in the last years, especially with ALMA observations, and we're waiting for James Webb ones, with James Webb latest results. But at redshift bigger than 3, still we know very little about that. And actually, the studies have been mostly done with the UV optical and near-infrared surveys for technical obvious reasons. So one of the reasons why it's interesting to go behind the dust is that also to study the interplay with the black hole accessory density and stuff. Another important thing is to understand the role of this, the origin of early type galaxies, and these radio-selected near-dark galaxies, the obscure galaxies, might play a fundamental role in galaxy formation and evolution from this perspective, because actually they have most of the characteristics that would explain the presence of these early type galaxies, even at redshift between 3 and 4, and it's highlighted passed in red in this formation scenario, which is the in situ formation by Rapi et al. 2018. So never underestimate the power of radio selection, but why? Because obviously there is no dust extinction, so you clearly see behind the dust. This also means that you're not affected by dust temperature biases and stuff. Moreover, given the larger wavelengths, you have a wider beam size, and also the wedding cake approach and the mosaic approach have been widely used and are very well known by the community, so they are like very consistent. Moreover, you can reach, as you do obviously with ALMA and with all the interferometry, you can reach very high resolutions, and you can most study the star formation and AGN. And here in this passage, the role of a panchromatic approach and the interplay with telescopes like ALMA and James Webb comes, because to understand what we are observing, obviously the best thing is combining different observations necessary to understand whether we have or not an AGN. So I will give you a bit of a taste of what has been happening in the Cosmos field thanks to the VLA 3 GHz project by Smolcic et al. But actually you will hear much better these things by Fabrizio Gentile tomorrow. So everything began with the work by Italia 2021, where they used this very deep, wide radio survey in the cosmos field to first study the star formation rate density by the so-called radio-selected near-dark sources, so the ones that have no near-infrared counterparts. And also we did the same in the work biennial 2022 in the Goose-Nord field, and in my submitted paper, I hope 2023. And what's doing Fabrizio Gentile. So we selected 272 galaxies in this field, and we used the wide band photometry to do SED fitting, to compute the median properties, and also doing single source studies. And then we derived the contribution of these galaxies to the star formation rate density. Also, just a quick reminder that a part of Cosmos will be observed by the James Webb Telescope. This is one of the main results, which is the median LCD. As you can see, we get median redshift of 3.3, so we expect to have very high redshift sources, which actually we found out with the single source LCD fitting, where we included also the A3 Cosmos data, also to understand a little information about the dust and the far infrared properties, and at the properties of an ultraluminous infrared galaxy. And this is the main result, which is the star formation, the contribution of these sources to the star formation rate density, where we found out that these sources actually contribute, and this is just actually a lower limit, of at least the 40% of the ones the UV selected ones. So actually it's promising, and that's also what makes you think maybe this radio selection is actually effective. So we should try to go deeper and to explore it inside new fields. We also found out that the number densities are consistent with the far ones of Chapman et al., for example, 2014, and other works of red and dead galaxies between redshift 3 and 4, and this leads back to the problem of the progenitors. But let's go to the new survey. So this is a very fast recap of what actually Quirino told you, and yeah, I felt like we should also thank the people who helped us there. We did many of our observations, both in Sydney and also actually remotely for these last months. And we got this deeper field, which has been chosen for having already a good, well-behaved map in the old 2 GHz survey. Moreover, we have the lens candidate, and it has been covered by many surveys that I will show you later. So first of all, as already Quirino showed you, we went deeper at 2 GHz, and this is the sensitivity at 4.5 sigmas, but not only, we also made a follow-up at 5.5 and 9 GHz and 16.2 and 20 GHz. Actually, these are 2 bands, so one of the advantages of APCA is that these 2 couple of bands, these are 2 things that can be observed all together. And this is the map at 5.5 gigahertz, the blue one, and overimposed are the 220 sources extracted at 2 gigahertz. And also the points in violet, yeah, the crimson color kind of points, are the detections at 20 gigahertz. So we are actually going towards, at least in a smaller region, because we used mosaics to cover the field, and we made a smaller region with the mosaic at 20 gigahertz. So we are going towards the ALMA wavelengths, in particular band 1, band 1, which we could exploit using the same technique that we used for the 20 years. So these are the very, very preliminary, I will show you what we expect and then the very, very preliminary results, because this data has been, we finished observing in January. Why we chose to do this follow-up at other wavelengths instead of going deeper at 2 years, because actually at these wavelengths, we could have some information on the age. We have some information of AGN versus not AGN. We can actually compute the spectral index of many of these sources. We can use, for example, and this is what I'm doing right now, the 2 GHz survey as a prior to find out sources at the other wavelengths. And because this is the region, and you can see by the picture where you have both the synchrotron and brainstorming, and you can understand which one is dominating. And it also gives the information on the star formation history, and obviously where it's radio, so where these wavelengths also you go behind the dust. This is also one of the core of this work, and it will become even more the most important part now. So understanding a number count, and this is another reason why we decided to observe this field at this wavelength, because we could target some self-forming galaxies at redshift bigger than 1.5. So we could also have more information about the expected number counts in the radio bands, which is also something that we still do not know, and it's great to understand it in particular in perspective of the SKA observatory. These are the very first results. This is the reliability at 5.5 gigahertz. Then we have, you can clearly see by this histogram, this is very clear that we have sub-millijansky, many sub-millijansky sources, and we also began starting to compute the first spectral indexes, because having a wide radio photometry, this is the very first thing that gives us immediate information about what we could expect to find in this blind survey. Another very cool thing is that actually, yes, there are some pointings of ALMA in this field, and also in this one field. This is one of the pointings. We found the 3 at the same in the same band, but they are a bit of offset. But Mattia Costello will for sure help us with their brand new technique to get as much information as we can. And on the right, actually, it's just a picture to show you, like, these are all the pointings by all the survey that I found, I've been finding covering this field. And actually, even this has been covered by even by some ASCAP fields, which is one of the pathfinders of SKA, to obviously Herschel, because it's the H-Atlas field. So yeah, we have a lot of Herschel data, which is fundamental for finding dust obscure sources. And let's go towards future perspectives.
3-minute warning.
Yeah, thank you. One of the things that we will be for surely do, actually we are doing it right now, is the SED fitting with this brand new system called Galapai by Ronconi et al. This is was our guinea pig, which is actually a galaxy from my older work in the cosmos field, but we already have a nice candidate to test it in the new survey. Then, as I told you, we will try to exploit the ALMA band 1 using the same technique at 20 GHz, because this will give us a lot of information, for example, on the continuum of dust and stuff. And the main result that we hope we will reach soon is having the radio number count, and then given the redshift, after redshift computation, study the radio luminosity function. So thanks, and this is all.
Thank you, Meriem. Any questions? Well, I can start. I think it's very interesting. I didn't quite understand the way you were selecting those 272 galaxies.
Yeah.
Was there some redshift range, or can you quickly review what was the basis?
We started from the VLA 3 years catalog by Smolcic. Later, then we only took kept the ones having no counterparts in the Cosmos 2015 catalog, adopting the same selection as Thalia 2021 in the Cosmos field. So they were selected actually not to be near infrared bright for the Cosmos 2015 catalog, because that's a near infrared selected catalog. So we included all the sources not having a counterpart in the near infrared. Moreover, actually in this, there were 476 sources in total. Then from them, I only extracted the ones that whose radio isophotes did not, 5 sigma isophotes did not intersect the 5 sigma isophotes of the near infrared map, chi-square near infrared maps in the Cosmos field. So yes, they are selected to be not as isolated as in the previous work by Thalia 2021, but at least with no near infrared contamination. I hope.
And do they end up in some redshift range? Is it of more than 3 or?
Oh, I can show you. I haven't the slide. This is the redshift distribution, and these are mostly photometric redshift. And actually, for some of them, we have now, but this is an ongoing work, some spectroscopic redshift. And since they were selected for not being visible in the near infrared bands, obviously we knew we were selecting higher redshift sources. So we don't have a peak, for example, under redshift 1.
Thank you.
You're welcome.
I check again. I don't see any hands. I have another question, okay?
Yeah.
Because I started to do some SED fitting myself for a project. So I noticed it said on one of the plots that showed median SED fitting that you use mag fees. So
Yeah.
does it mean these 272 galaxies were non-AGN, or I think mag fees doesn't include AGN.
There is a version.
Right.
We use the non-AGN one. And actually, before giving some constraints on the SED and stuff, we also did, yeah, because this is the hidden slide. We also actually tried to understand the contamination region. This round figure is the stacking in Chandra. In the Chandra band, we used the C-stack tool, and we got that the X-ray luminosity is compatible with the star formation. So there is no at least need of AGN. Then we also made some diagnostic diagram which used the far infrared radio correlation. Obviously, there is no powerful visible AGN by that, but this actually doesn't mean that there is not a burning AGN without jets yet. But this is something that actually only deep X-ray observations, very deep X-ray observations will tell us, but it's not likely to have them, unfortunately.
Thank you so much. I see a hand. Go ahead, Abdi.
Yeah, thanks for the great talk. Looking at this plot that you're showing with the photometric redshift, can you explain why there is a big dip at redshift of 2?
Actually, it's more like a binning thing of the redshift. So it's not for physical reasons.
Okay. Yeah, it was kind of surprising that you have such a gap at redshift.
Yeah, yeah.
Okay, thanks.
Any questions? I check the feed in the chat. Well, thank you again for your wonderful talk. And I'll probably post questions on the Slack if you are there.
Thank you.
Because it's interesting for me. And good luck with your 2023. We hope for that for you, for your paper.